Hey everyone, Mr. Fritz here. In this video, we're going to talk about vectors in the component form. We just did a couple bearing examples, and now we're going to kind of dig into what I think is an even easier way to conceptualize vectors rather than just drawing them on grids. We can use this thing called component form. And before we take any notes or rewrite anything down, I want you to look at these two vectors that I've drawn. They're the same exact vector. They each have the same length, and they each are going in the same direction. So they're exactly the same. But if I were to hold these two up to you, think about which one would be easier to describe to somebody who's not looking at this vector. Do you think it would be easier to describe the one on the left or the one on the right? What sort of attributes could you talk about with this vector versus this vector? Which of these do you think would be easier to redraw? If I just showed you a picture of this one and said go ahead and draw it, would that be as easy or easier or more difficult than if I showed you this picture and I asked you to redraw it? Hopefully, if you're like me, I like this vector better. I think it's easier to draw. When I'm drawing this vector, I'm counting boxes. I'm counting how many I'm going down, counting how many I'm going over. This is just kind of floating in the air. I need to use a ruler, I need to measure it, I maybe need a protractor to find the angle. I like this vector better than this one. And if you're like me and you agree, then you're going to love component form. Let's go back to what we know about vectors. We know two things that makes a vector. One of them is a vector has to have a length. So this vector has a length. In this case, it's 80. I'm going to move this over. Oops. I'm going to move this over here. It has a length, and it also has a direction. In this case, it's a bearing of 45 degrees. But what is another way that we can describe this? Well, we can describe this by breaking it down into what we call component parts. And by breaking it down into components, basically what we're going to do is we're going to look at the horizontal distance of this vector and the vertical distance of this vector. It's almost like we're taking this vector and we're making it the resultant of a sum of a horizontal vector plus a vertical vector. So it's kind of like we're treating it as if it's a resultant. We can treat all vectors as the resultant of a horizontal and a vertical vector. Now, we want to kind of figure out what these values are. Let's call this A, and now actually, since this is a 45-degree angle, this really makes a 45, 45, 90. So both of these have a distance of A. And if we wanted to find what the horizontal and vertical piece is, we can just use the Pythagorean theorem, and we could say that A squared plus A squared equals 80 squared. And so that's going to be 2A squared equals 80 squared, and if you work out the math here, I think A is going to equal about 56.6. And so really what that means is we've broken this down into a horizontal and a vertical component. This is going to be about a horizontal component of 56.6, and this is a vertical component of 56.6. So if you were to take 56.6 steps in a horizontal distance and then 56.6 steps in a vertical distance, it's as if you took 80 steps at a 45-degree angle. Why is this helpful to us? In general, we can write any vector in component form. We can think of it as an x component and a y component. We're turning this into a right triangle. We know how to use right triangles. We know how to find all kinds of angles and side lengths of a right triangle, so we like right triangles. You're going to see this notation here, this bracket, or these vertical square brackets. That's what notates a vector. The top number is going to be the x, the bottom number is going to be the y. So let's talk about just how to draw these things. If I were given the vector 2, 3, we could draw it as going over 2, going up 3, and then the vector is, kind of think of it as almost the resultant between these two components. You can read this as that 2 is the horizontal step and 3 is the vertical step if I were to start with this vector and break it down into components. So in this form, we're kind of given the components, but I could also start with a vector and break it into its components. So let's see an example about how to draw these vectors. Remember, the vectors, it doesn't matter where they start from. I can start anywhere I want. And this means that I'm going to have a horizontal component in the positive direction, 3, and I'm going to have a vertical component that's in the positive direction, 4. So let's start it right here. And I like to think about 1, 2, 3 over, and 1, 2, 3, 4 up. This is going to be my vector, just like this. With this vector here, same thing. Let's start it right here. And I'm going to go over 2, 1, 2, and down 1, 2, 3, 4, 5. This is where I'm going to end. This is the vector given by these components. So that's basically it. Really, you just have to remember that the horizontal's on top and the vertical's on bottom, and you're ready to draw these things. So why don't you try a couple examples. Pause the video and draw arrow diagrams to represent these vectors. All right, here are the answers to the U-Try problems. Check them out. Again, they don't have to start where I started them. They can be anywhere you want, but they should have this general size and direction. Why don't you try another example? Now this one, we are starting with the vectors, and I want you to come up with the component form with this bracket notation to figure out how to describe both of these two vectors. And here's what those answers look like. So hopefully you got it. Let's keep moving here, and let's talk about adding vectors. The reason why I love component form of vectors is because adding them is super simple. All we need to do is we need to draw the vectors, well, actually, we're not even going to need to draw them, but let's think about if we were to draw them using the old school method. If I were to add vector A, let's draw vector A. That's to the right. Let's start it here. And so we're going to go to the right 1, 2, 3, and up 1, 2. This would be my vector A. And let's add to that vector B. And according to this, vector B is to the right 1 and up 4. 1, 2, 3, 4. That's B. So vector A plus B is going to be this resultant right here. So this is what it looks like graphically. And let's think about what it would look like by adding component vectors. If I want to add two vectors, A plus B, that's the same thing as adding the component form 3, 2 plus 1, 4. Oops, not 1/4. 1 and 4. And if you kind of see what's going on here, if I were to analyze using my graph, in purple, I went over a total of 1, 2, 3, 4 in the horizontal direction, and I went up a total of 1, 2, 3, 4, 5, 6 in the vertical direction. So the vector A plus B, we already know, is going to come out to be 4, 6. And hopefully we're seeing that this is coming from adding the horizontal components together of vectors A and B, and adding the vertical components together of vectors A and B. This is exactly where this 4, 6 comes from. So now I don't need to draw this in this grid. I can just add the horizontal components together, add the vertical components together. That's it, adding vectors in component form. So in general, if I have these two vectors, A and B, then I can add them up using this notation here. So pretty straightforward. Let's think about negative vectors. We're going to move towards subtraction with vectors, but let's think about, again, reminding ourselves what negative vectors look like. Because you don't really have, when you subtract vectors, really think about adding negatives. So if I have a vector 2, 3, here's my vector, I can construct the negative vector, which would be just the opposite direction in the horizontal component and the opposite direction in the vertical component. So this would be my negative A. And hopefully you're seeing here that the vector negative A is the same thing as the negative of the original components for vector A. And so in general, if I wanted to take a negative vector, I basically just negate both of the components. Now why is this helpful? For vector subtraction. So remember, I'm going to add the negative to subtract. If I want to take A minus B, I'm basically going to take vector A and add to it, by drawing the tip to tail, the negative of whatever vector B is. So if I start again over here for vector A, let's go back to blue. I like blue for A. I'm going to start here and let's go to the right 1, 2, 3 and up 1, 2. Here is vector A. And if this is vector B, then negative B should equal negative 1, negative 4. So let's add that to vector A. I'm going to add a -1 in the horizontal direction and a -1, 2, 3, 4 in the vertical direction. This is negative b. So the sum of these two vectors is going to be this resultant right here, from my starting point to my ending point. And this is a minus b. And hopefully we're seeing here that when I take vector a and I subtract vector b, that's the same thing as taking the components of a and subtracting the components from b. So this is the same thing as taking 3 minus 1 and 2 minus 4. So that should be, this vector a minus b is 2, negative 2. And hopefully you're seeing that. I'm going to the right 2 and down 2. That seems to match up with the graph. So there's my vector subtraction. So in general, we have this statement right here. Two vectors, if I subtract them, I'm just subtracting their components. So let's see another example of this. Let's do these three examples here where I want to subtract all these vectors. In this case, I want to add them. So if I'm going to put this together, let's just do this kind of quickly. Vector p is going to be -4, 2, and I'm going to subtract vector q, which is -1, -5. I'm going to combine them together and subtract the components. So -4 minus -1, and then 2 minus -5. So the difference between these two vectors, or the sum, I guess, of p and negative q is going to be, that would be -4 plus 1, so that's -3, and then 2 plus 5 is 7. That's my first example. Let's keep rolling here, and I'm going to subtract q by r. So I'm going to take vector q, which is -1, -5, and subtract r, 3, -2. So that's going to be -1 minus 3 and -5 minus -2. That's what I get when I combine these vectors. So vector q minus vector r is going to be -4 and then -3. That's it for that one. And finally, I've got a threefer. 3 vectors. So let's take p, -4, 2, plus q, which is -1, -5, minus r, -3, oops, sorry, just 3, and then -2. Smush it all together, and I have -4 minus 1 minus 3, and 2 minus 5 minus -2. And I put all of this together, and this looks like that's going to be a -8 on top. And this is a 2, say 2 plus 2, that's a 4 minus 5, that's a -1. Hopefully I did that right. So those are my 3 examples. I want you to give this a shot. Same type of deal, 3 vectors, perform these 3 operations, these sums or differences, and see what you come out with. And here are my answers for this U-try problem. Check over the work. I might have done this slightly differently than I showed in the example, but it really doesn't matter how you slice it. It should come out to be these 3 solutions down here. So hopefully that went all right. Let's see another example now where we're doing the same type of thing, but now we're actually going to be taking scalar products of these vectors. So we've done that graphically. We're going to do that with the component form. But let's think back to the graph for a second. If I have some vector, let's call it A, and it looks like this. If I wanted to graph 3A, it's basically 3 of these vectors together. So altogether, this has become vector 3A, right? That's this entire piece. Now, wouldn't it make sense that I can take all the horizontal components, add them up, and all of the vertical components, and add them up, and still get vector 3A. This is basically 3 of my horizontal components, and this is 3 of my vertical components. So this is going to be just like taking a negative vector, where I'm going to multiply the scalar by the horizontal component and the vertical component. And it's really as easy as that. So if I take -3 times vector p, it's, again, we have to think like there's not really I'm taking like the negative of vector p and multiplying that by 3. So it seems kind of like weird to break it into those parts, but you can't have a negative vector in the sense that you can have a negative number. It's just like the opposite direction, but 3 times as big. That's kind of how I want you to think about this. Anyways, the process looks like negative 3 times the components 1, 5, or this is going to equal negative 3 times 1, and then negative 3 times 5. So this is going to be the vector, the resultant will be negative 3, negative 15. For this next one, I want to take 1/2 of vector q. Vector q is negative 2, 4. So I'm going to do the same thing here. This is going to be 1/2 times negative 2, and then 1/2 times 4. So the resultant vector here is going to be negative 1 and 2. Finally, I want to take 2p, 2 times vector p, which is 1, 5, and I want to add that to vector q, which is negative 2, 4. And I'm going to combine this kind of all into one step here. I'm going to take one big vector of 2 times 1 plus negative 2, and I'm going to take 2 times 5 plus 4. So I basically kind of combine multiplying the scalar to both of these components and then adding these components together, kind of all at once. Hopefully that makes some sense. So in total, this is going to be a 2 plus a negative 2, so that's 0, a 10 plus a 4, that's a 14. This is my resultant vector from 2p plus q. All right. Hopefully that makes some sense. Why don't we take a break here, and when we come back, we're going to finish this out with the length of the vector. How do we find lengths of vectors in component form? So we'll check that out in the next video.